Hello, viewers. In this class, we're going to look at uh, a derivative, that is differentiation. Okay, here we're going to start with uh, how to find the derivative of the function from the first principle. Okay, that will be our topic, and we know, for instance, if we have y is equal to ax raised to power n, we know that our first derivative here, the y, the x, is n a x raised to power n minus 1. Okay, in this class, from first principle, we are going to derive, show that the y dx is exactly this. Okay, from first principle, if we have here your y here is y plus delta y. Okay, and x is x plus delta x. Okay, that is the change. So your y plus change in y, your x is x plus change in x. So we're going to use this path, to establish the derivative of y is equal to a x raised to power n. Okay, now here let's begin the class. We know that y is equal to ax raised to power n. That is a function. So, and I said that your y there, it will become y plus delta y plus delta y, and we have a open bracket. In place of x, we are putting x plus delta x, close our bracket, raised to power n. So our x plus delta x raised to power n, and the next thing is that we move the y, we leave only delta y on the left hand side, and we move y to the right hand side. This become x open bracket x plus delta x all raised to power n minus y. We know that y is a x raised to power n, so that delta y on the left hand side is equal to a open bracket x plus delta x raised to power n minus a x raised to power n. Now our interest is how to expand x plus delta x all raised to power n. This is a very crucial aspect of what we need to do here. Now here we're going to use the binomial expansion here. But first thing, we know we're going to use binomial expansion, but we also have to adopt the combination rules here. So here, if we are to expand this, there are coefficients of x and delta x that must be noted, and the highest power of n for x, the highest power will be x raised to power n. The same thing, the highest power of delta x will also be delta x raised to power n. So what that simply means that if we have an x plus delta x raised to power 2, for instance, the highest power of x will be 2, and the highest power of delta x will also be 2. So with that idea, we adopt it here. But in combination, we know the coefficient of x and delta x is n combination r. We have a raised to power n minus r times b raised to power r. Here, our a here is x, and our b is delta x. And we should also know that r is moving from 0 till you get to n. Okay, so we will use this fact to expand this. Okay, because the highest power of our expansion is n. That means we were going to develop some manipulations. Okay, now if n, also know that n, our first expansion is n combination 0. That's when r is 0. Then we are going to have a x raised to power n minus 0, and then b raised to power 0. So our delta x at this point is raised to power 0. Okay, and anything raised to power, number raised to power 0 is 1. So here we're going to have a n combination 0, s raised to power n, and n combination 0 simply means n combination 0. Let's expand it, is n factorial. Please let me put it here. N combination arrow simply means n factorial all over n minus r factorial bracket r factorial. This is the formula. So please your n combination 0 will become n factorial all over n minus 0 factorial bracket 0 factorial. So here we have our n factorial. N minus 0 is 0 is n. That will give us n factorial 2, then 0 factorial. So n factorial go with n factorial, and we know that 0 factorial is 1. So it simply means that in this our expansion here, in the expansion of this expansion, so this will become x raised to power n plus, okay. Now we're going to look at when r is equals to 1. When r is equals to 1. So r is 1. When r is 1, and look at our expansion here. This become n combination 1. Okay, so here we have a x raised to power n minus 1. Then theta x raised to power 1 there. Okay, here n combination 1. Let's quickly look at n combination. N combination 1 simply means n factorial all over n minus 1 close bracket factorial, then 1 factorial. Okay, now we need to expand this. This n factorial simply means we can also expand it as n into n minus 1. No continuous like that. But since we're having n plus 1 at the denominator of n minus 1 at the denominator, n minus 1 factorial at the denominator, what we need to do, we stop there. So this will become n into n minus 1 close bracket factorial all over n minus 1 factorial at the denominator, so that this will be off. So at this point in time, for n combination 1, our result there, the coefficient of this is n. So here we have a n open n x raised to power n minus 1 delta x. Okay, the next aspect is, we are still going to look at when r is 2. So that will quickly give us n combination 2, which is n factorial all over n minus 2 factorial bracket 2 factorial. Okay, here we also expand this. This n factorial will become n into n minus 1 close bracket n minus 2. We will stop there because at our denominator we have n minus 2 factorial there. So we stop there, so that here we now have n minus 2 factorial bracket 2 factorial. So that this will go with this. So that what we're going to have here as the coefficient of x and delta x there will be n open bracket n minus 1 all over 2. We have a x, we say n minus arrow is 2, so that we have a n minus 2. Then our delta x all square. If we continue this process, it will continue like that. So instead, we put three dots, and the last coefficient here will be plus delta x all raised to power n. Okay, so the expansion of x, open bracket, s plus delta s all raised to power n is s raised to power n plus n x raised to power n minus 1 delta s plus n into n minus 1 close bracket s raised to power n minus 2 open bracket delta x close bracket square all over 2 plus continue till delta s raised to power n. So we replace the whole of this in place of this. So what will happen here is we have a delta y is equals to this is outside, so all the term here we have a x raised to power n plus n x raised to power n minus 1 delta x plus n into n minus 1 all over 2 x raised to power n minus 2 delta x all square plus plus delta x all raised to power n with large bracket here minus a s raised to power what n. So this a outside here will affect everything in this bracket, and this will become on the left hand side we have a delta y. This will become a s raised to power n plus a n s raised to power n minus 1 delta x plus a n open bracket n minus 1 all over 2 x raised to power n minus 2 delta x all square plus plus a delta x all raised to power n minus a s raised to power n. So here we see that this a x raised to power n and minus e x raised to power n, they are off. So we'll be left with the other distance, and our distance we are trying to look for delta y over delta x. So we divide through by delta x, and if we do that, here we have a delta x, here we have a divide by delta x, dots till here we have a open bracket delta x raised to power n divide delta x. Okay, divide delta x. So here we see that this and this will be off. Here we have a delta x square, one will be off, we will be left with just one delta x here. Here we will have a delta x. In this part we have a delta x n minus 1, because if we apply the law of indices here, common base, this raised by 1, that means n minus 1, because there's a division line here. So, and we know that as the limit of delta x tend to 0, we will now find out that the y over delta s, delta y, delta x will become the y the x. Here, what will be left here, we will have a n x raised to power n minus 1. Here, there is 1 delta x here. If you put 0 here, that means all this one will blow off. Similarly, this one will blow off, and our dy ds will become ax s raised to power n minus 1. That is why we say that dy ds of this function is na x raised to power n minus 1. Okay, this is how we expand this from the first principle. Please, all you help me do, try as much as possible, help me subscribe and also share to other platform. Have a nice time. See you in our next virtual class.